Hello students, welcome to the class. Today we will see the section 4.4 of the NCERT, which is of the chemical bonding chapter theory part 5. So this is the disclaimer. Today's objective would be to see the VSEPR theory. Now we have already dealt with the postulates of the VSEPR theory. Those same postulates are to be applied to predict the geometry of simple molecules. Now the problem is that predicting directly with the help of those postulates may pose a difficulty to you. So instead of that, on a regular basis, we use the formula of steric number to calculate the number of bond pair and lone pair and so on, and then we use it to predict the structure. So we will look onto that with some examples, right? And after that, I will use this VSEPR theory to predict the shape and geometry of some molecules, and then I will compare the polarization of the bonds, right? So that is the important part. I will go on to that. So I have not got into the depth of the polarity because at that time we were unaware about the structure. But after covering this lecture, we will be able to determine the structure and therefore we can compare the polarities. Okay. So with this, let us move on to the VSEPR theories and see that how can we predict the shape and geometry of a molecule. So there are three simple steps that you can use to do the same. Now in this thing, two things are to be determined. The first is molecular geometry, and it includes both the bonding pair and the lone pair. Okay. The second thing is molecular shape, which excludes the lone pair. So this thing will be more clear when we will move on to the discussion of the shapes. But for now, you should remember two things. Okay. So if you are considering the geometry, you should compare you should see the position of the lone pair and the bond pair both. And if you are looking at the molecular shape, you have to exclude the lone pairs. Now, what are those steps? The first step is, of course, drawing the Lewis structure. So first of all, whenever you see a molecule, just draw the Lewis structure of that molecule. Then in the next step, determine the steric number. So I will give you a formula for determining the same. It's very simple. And once you got your steric number, you have to arrange your atoms and your lone pair according to the steric number that you have obtained. So our first part is already clear to us, which is about drawing the Lewis structure. We have already talked about this in the previous class, so I will not go on to that. I will try to explain that how you will determine the steric number. So talking about the steric number part, it can be calculated by using this very simple formula, which says that 1 by 2 multiplied by V plus M minus C plus A. Now what are these symbols? The first symbol, which is V, it is simply equals to the number of valence electron of the central atom. So if you consider a molecule, there will be various atoms in that. If you are considering H2O, NH3, SO2, then it includes various other atoms. Now you have to determine that which one is a central atom. So the general idea is that the central atom is less electronegative, but this concept of putting the central atom as less electronegative one is not applicable to the hydrogen. Suppose you are taking the NH3, then in that case your hydrogen is less electronegative, but it cannot be taken as central atom. But if you take a molecule like SO2, then in that your sulfur is less electronegative as compared to oxygen, so it will be in the center. Okay, so remember this, that except hydrogen, if there is a hydrogen in a molecule, then this rule is not applicable. But if it is not there, you can always take the less electronegative element as the central atom. Now, second is M. The second term here, you can see it is M, which is equals to the number of monovalent atoms. Okay, so monovalent atoms means those atoms which have a valency of 1. Example, you can take hydrogen, you can take fluorine for that, you can take chlorine for that. So all of these are having a valency of 1. Now, these monovalent atoms which are present around the central atom are termed as surrounding atoms. Got it? Then after that we have C, which is cationic charge, and then we have A, which is anionic charge. So cationic charge is the positive charge that is enclosed upon the molecule, and the negative charge is represented as ionic charge. So you will add the ionic charge and subtract the cationic charge. You can remember all of this with a simple term, VMCA. So half into VMCA, if we have a negative in middle and positive on both sides. Got it? Okay. So let us try to apply this formula on different molecules. Now, in the first part of the lecture, I will try to deal with those molecules that have only bonded electrons around the central atom. Okay. So I will not take that molecule which has a I would say lone pair around the central atom. So about those molecules, we have to talk about the repulsion and all. So I will deal with it later on. So first, let us apply this formula onto simple molecules which have no lone pair on the central atom. So I am writing this formula on the top so that you are not confused about it while I am applying it, because it is new to you. So let us take the case of carbon dioxide. Okay. So this will be the Lewis structure of carbon dioxide. I think there would be no difficulty in drawing the same. It's very simple to draw. Okay. So this is the Lewis structure of CO2. Now what we will do? First we need the V, which is the number of valence electron on the central atom. Now if you compare carbon and oxygen, so your carbon is less electronegative. So therefore it will be in the center, and it is in the center. I guess it is clear to you. Now we will calculate the number of valence electron in the carbon. So it's very easy to do so. So on the central atom carbon, we have 4 electrons, right? So we know the configuration of carbon. It will easily tell you that the valence electron is 4 on the central atom, which is carbon. Then what is the number of monovalent atoms? So why are we saying that the number of monovalent atoms is 0? Means there is no surrounding atom that has a valency of 1. Because we know it very well that the electronic configuration of oxygen clearly depicts that it needs 2 more electrons to complete its octet, right? So it has a valency of 2. Therefore, the number of monovalent atoms will be 0. I would suggest you to think of atoms which have a monovalency. So there are many examples of it. So meanwhile, we got these 2 things, which is valence electron and number of monovalent atoms. Yes, the example would be lithium, sodium, potassium. Yes. Can you think of non-metals also? So here in this case, we can think of non-metals as chlorine, fluorine, and so on. Right? Now moving on to the charge, there is clearly no charge on this carbon dioxide. It is completely neutral. Therefore, we can calculate the final steric number. So what will be the steric number if you put all these values here? This steric number will come out to be 2. Got it? So till now we have not talked about that which steric number is associated with which shape or geometry. So now I am only giving you the method to calculate the steric number. Then I will provide you a table for that. And after that we will see that what are the shapes of this given molecules. I guess this is clear to you. The calculation of steric number, it's very easy to do. Now moving on to the next simple molecule. So our next molecule is boron fluoride, okay, which is BF3. If you draw the Lewis structure of this BF3, it will look like this. Okay, so 3 electrons are there in the outermost shell of boron. So it will share its electron with each of the fluorine, and that will result in a single bond between boron and fluorine. So 3 single bonds are there. Now let us look for the values of the formulas constants, which is V, M, C and A. Since the central atom is boron, as it is less electronegative as compared to the fluorine, so we can say that the valence electron on boron is 3. Got it? Then what is the number of monovalent atoms? We know it very well that fluorine is a monovalent one. Therefore, the number of monovalent atoms in BF3 will be 3. Again, the charge is 0. The molecule is completely neutral. So we can put all of these values in the above formula to calculate the final value of the steric number for the BF3. If you put all this, you will get your steric number as 3. I guess this is clear to you. It's very simple to calculate. Okay. So why are we saying that monovalent atom is 3? Because if you look at fluorine, it is a monovalent one. And why it is a monovalent one? Because it needs 1 electron to complete its octet. So it is a monovalent atom. So A is the anionic charge, C is the cationic charge. Okay, so there are no charges on it. So cationic means positive charges and A anionic means negative charges. Since the charge is 0, we are taking both of these values as 0. I hope this is clear to you. Now let us move on to the next one. So the next example is of ammonium ion. Now if you draw the Lewis structure of ammonium ion, then how many single bonds would be formed between the nitrogen and hydrogen? Of course, there will be only single bond possible. So what are the number of single bonds possible for NH4+? It's very simple. The number of single bonds would be 4. Now there is a very important thing in its Lewis structure. All of the bonds that are present in ammonium ion are not purely covalent. So one of them is coordinate bond, or you can say it as what? Coordinate bond or divalent bond. So the positive sign on the hydrogen. Okay, so there is a positive sign, you know it very well. So that positive sign is on this hydrogen. So it has no electron to share with the nitrogen. So it is taking both of the electrons, remaining electrons of nitrogen, and making a coordinate bond here. So it's very important to see this, right? It's an important thing. Now, if this is the Lewis structure, so we can easily say that 4 bonds are to be arranged in a proper manner. And for arranging it, we will determine the steric number. So let's see the steric number here. If you consider it for the central atom, so once you got the Lewis structure, you can easily predict the steric number also. From this diagram, it is very clear the steric number would be 4 because 4 bonds are there. Now remember, what is the steric number of CO2? It was 2. Now why it was 2? There were 4 bonds in it. So to counter that fact, we should remember that the double bond is considered as single bond. Therefore, in case of CO2, although there were 4 bonds, but 2 of them were double. So we considered them as single, and hence we got the steric number as 2. I guess this is clear to you, right? So this is very important to understand that your CO2 is having a steric number of 2, although it is having 2 bonds extra. And those 2 are double bonds. So we cannot consider as them single entity for calculating the steric number, because our VSEPR theory clearly says that if you have a double bond, take it as single bond. I hope this is clear to you. Now here if you see, then you can clearly see that hydrogen is less electronegative, but still it is present as surrounding atom. Why? Because it is an exception. In all the cases, mostly your central atom is less electronegative, except in this case because it's a hydrogen. Now since your central atom is nitrogen, what will be the number of valence electron? It would be 5. Okay. Then what is the number of monovalent atoms? Your hydrogen needs a valence electron of 1. So it has a valency of 1. Therefore, we can keep it in under the number of monovalent atoms. Okay. Yes, you will also consider the triple bond as single bond. Whenever you see a multiple bond, never consider them as the different bonds. You can take the case of ethine, right? So if you take the case of ethine, your carbon would be sp hybridized. It has 4 bonds. Okay, one carbon has 4 bonds, and it's very clear. But since one of the 3 bond is paired as the triple bond, therefore it has a steric number of 2 only. You can try and calculate it for ethine, right? Now, here you can see that it has a positive charge. Once you are given the molecule, that means you are knowing about its charge. So you will be given in the exam that what should be the shape of the ammonium ion. Now you should know it, that your ammonium ion is a positively charged species. Okay. And there is no way you can draw the structure of 4 hydrogen atoms with nitrogen without taking a positive charge. If you take it, it will give you a very wrong type of structure or odd electron type structure, which is rare, right? So it is already given in the molecule that it has a positive charge on the top. Got it? Now, if your positive charge is +1, then we can take the value of C as +1, okay, because the cationic charge is +1, and we can put this value here. If you put this value and calculate the steric number, you will get half into 5 plus 4 minus 1. Why we are doing -1? Because there is a charge of +1. And we know that cationic charge are to be subtracted. This will give you the steric number of 4. Is it clear? I hope it is clear to all of you. Now moving on to the prediction of the shape with the help of this steric number. Now we know that how to calculate the steric number. It's very simple. We just have to know the total number of valence electron around the central atom, the number of monovalent atom, the cationic charge and the anionic charge, and then we can easily calculate the steric number. Now moving on to the geometries that are related to different steric number. If your steric number is 2, then your shape or geometry both will be linear. Now, we are seeing here 2 terms, shape and geometry. It's very important to differentiate between these two during the examination time. So, in case of molecules that have no lone pair on the central atom, the shape and geometry are same. Okay. So, if you take the case of CO2, which you have seen just now, or the ammonium ion, all have 0 lone pairs on the central atom. Therefore, you can take the shape and geometry of all those molecules as same. If you're so considering that thing in point, which has no lone pair, see it is written here clearly that in this case, there are no lone pair of electrons on the central atom. Then in that case, if your steric number is 2, then your shape and geometry would be linear. So what you can tell about the CO2, whose steric number was 2, it is a linear molecule. If you consider the next steric number, which is 3, then in that case, the shape or geometry will be trigonal planar. Now the important part is angle. In the case of linear molecule, the angle is 180 degrees. Whereas in case of trigonal planar, it is 120 degrees. It's very simple to guess. Since there are 3 divisions, if you look here, there are 3 divisions, right? And the total round of angle is 360. So 360 divided by 3 will give you 120 degrees. Okay. Similarly, for the case of 4 steric number, the shape is tetrahedral. And if there are no lone pairs, then in that case, your angle would be 109.5 degrees. Okay. So all of these angles are only applicable if the number of lone pair on the central atom is 0. Got it? And how do you know that? Just draw the Lewis structure and you will understand that which has a lone pair on the central atom, which molecule has a lone pair on the central atom. I hope this is clear to you. So there are 3 steric number. 2 is for linear, 3 is for trigonal planar, and 4 is for tetrahedral. Okay. Moving on to the next question. So, what is the next steric number? 2, 3, and 4 are being covered. 5 and 6 are also given in your NCERT book. So, for the 5th steric number, the trigonal pyramidal will be the shape, and there will be 2 kinds of steric number here. What are those 2 kinds? One is of 120 degree and the second one is of 90 degrees. Okay. And if you look at the octahedral, it is having a steric number of 6, where again there are only one angle which is 90 degree everywhere. Okay. So BF3 has an angle of 120 degrees and not 90. Okay. So this is not possible because BF3 has a steric number of 3. So total angle in the tetrahedral would be 720. Yes, that's true. Now, I guess you got that what are the steric number and what are their relevant structure. So again, I am repeating it all. The one has a shape of linear. Sorry, steric number 2 has a shape and geometry of linear. 3 has a shape and geometry of trigonal planar. 4 has of tetrahedral. 5 is of trigonal pyramidal. And 6 is of octahedral. Okay. Now let us move on to those molecules which have lone pairs. So our next target is inclusion of this lone pairs. Before moving on to that inclusion, let us look at the molecules whose steric number were calculated in the previous discussion. If the steric number are being calculated correctly, then we can easily predict their shape based on our previous discussion. For NH4+, the steric number that we got was of 4. So it will be a tetrahedral one and the angle would be 109.5 degrees. Whereas in case of CO2, the steric number is 2. So it will be of linear shape. Now see here, the CO2 has 4 bonds, but this double bond and this double bond, both are being considered as a single bond, and therefore 2 single bonds will contribute to 2 steric number. And lastly, for the case of BF3, you can see 3 bonds are there. So steric number is 3 and the angle would be 120 degrees. Okay. And the shape would be trigonal planar. I hope this part is clear to you. You don't have any doubt right now. So if you have a doubt, you can just join the forum and post your doubt there. Now let us include the lone pair in our discussion. So this is the most important part. Mostly the questions are asked from this part where our lone pairs are being included. If I talk about the lone pair, we know it very well that the lone pair are localized on the central atom. Okay, they are not shared between the central atom and the surrounding atom. They are only present on the central atom. And that is the reason we call them as lone pair. Now, each bonded pair, we know it is shared between 2 atoms. So that makes the difference between the electronic distribution of lone pair. Again, I am repeating it. Your lone pair is always localized on the central atom, whereas your shared pair of atom is between the 2 atoms. And while determining the shape, in most of the cases, we are interested in the number of lone pair of the central atom and not the surrounding atom. Okay, so we will talk about that. There is an impact of that, but for now it has no impact for the simple molecules. This was the order that we got from the postulate. The repulsion is maximum between the lone pair, then intermediate between the lone pair and the bond pair, and the least between the bond pair and the bond pair. So this was the order that we got. So what we can say that due to greater repulsion of the lone pair, there is deviation from the idealized shape. Now what is the meaning of this idealized shape? if you take the ideal shape of trigonal planar, then what would be the angle of that trigonal planar? It would be 120 degree. But if you look at a molecule which have both lone pair and the bonded pair, then the angle would not be same. Okay, there will be deviation from the ideal case. The previous molecules that we discussed earlier, all those have no lone pair on the central atom. But if as soon as we introduce the lone pair, there will be deviation from the ideal shapes. And the reason is also very simple. It is due to the greater repulsion that alters our bond angle in the molecules. Now let us look at some examples to justify this argument. Okay, so we have seen some arguments right now. Let us look at some molecules to justify the same. So the first molecule that I will take would be sulfur dioxide. If you consider the Lewis structure of sulfur dioxide, you can easily see that your central atom is having a lone pair of electron. Okay, so 2 electrons are there. We can call it as one lone pair. Now its shape would be not so simple. You can see that according to the steric number, if you look, it will have steric number of 2. So the shape should be linear, right? So that would be the normal case. But it is not so. So let us calculate the steric number first of all. If you use our general formula and calculate the steric number and not by just looking at the Lewis structure, you will not get it as 2. Instead of that, what you will get? You will get the valence electron as 6. Number of monovalent atoms are 0 here because the atom is oxygen, which is divalent. And charges are 0. So on doing the calculation, you will get the steric number as 3. So now you got the steric number as 3. But if you consider your previous case, according to the number of bonds, you will say that no, it should have a steric number of 2. Okay. So let us say it has a steric number of 3. We have calculated it. It's our formula. So if it is the formula, then the shape would be what? The shape should be trigonal planar. So this is our theoretical shape that we will consider. But in the reality, this thing is completely different. Okay. The shape is never the trigonal planar for the SO2. Now let us take the actual case and compare it with the previous case. With the help of sophisticated techniques, it was seen that your sulfur dioxide has a bent shape. Now what is the meaning of this bent shape? So this is the bent shape that we see. If you look at this Lewis structure here, then this lone pair is repelling this bond pair. Okay. As a result, the angle which should be 120 degrees, it is being reduced to 119 degrees. So the value is being reduced by 1. Why it is happening? Because this lone pair is pushing this bond pair and this bond pair, and therefore reducing the angle between them. I hope this is clear to you that why it is happening. You have seen in the Lewis structure that sulfur has a lone pair. So this is the lone pair and it is repelling and reducing the angle of sulfur dioxide. As a result, we will say that the shape is not trigonal planar. Instead, it is bent. But if you are considering the geometry, remember in the starting of the chapter, I said that while you are considering the geometry, you have to take the lone pair. And if you consider the lone pair, it will look simply like a trigonal planar. So what we can say that in case of molecules which has a lone pair, the shape is different and the geometry is different. The shape is bent here and the geometry is trigonal planar here. Okay. And what is the reason? The reason is that the bond pair repulsion is less than the lone pair repulsion, and due to which our angle is being reduced to 119 degrees. Okay, and if I take it accurate, it would be 119.5 degrees for the SO2 molecule. Okay. Now, moving on to the next molecule, which again has a lone pair on the central atom. The example is of ammonia. So this is the Lewis structure of ammonia. Now you can clearly see that the central atom has a lone pair on the nitrogen atom. Okay, so its shape would be different from the predicted one. Central atom is nitrogen, of course, because the hydrogen is the one which is present as surrounding atom. And the valence electron on nitrogen is 5. The number of monovalent atoms would be 3. Okay. Therefore, since the charges is 0, we can calculate the steric number as 4 here. Okay. So the steric number is 4. I guess it is easy to calculate, but if we look at the steric Lewis structure, it is very clear that the Lewis structure is not depicting a 4 steric number. And this is clearly due to the inclusion of lone pair. But if it is having a steric number of 4, then the shape should be tetrahedral. Okay, so what is the theoretical shape? It should be tetrahedral. But in reality, the shape is not tetrahedral. Instead of that, this ammonia molecule has a shape of trigonal pyramidal. Now, this is very interesting shape. You must be seeing it the first time. So this is the shape of that. Okay. If I do not consider the lone pair and simply consider this NH3 molecule, then it is looking like a pyramid. There are 3 hydrogen atoms and 1 on the top. So this is a trigonal pyramid. But if you consider the lone pair as well, your shape would be different. Or I would say not your shape, your geometry would be different. And that geometry would be tetrahedral. So we can easily now differentiate between the shape and geometry in case of the NH3 also, because it has a lone pair. So the actual shape is trigonal pyramidal and the geometry is tetrahedral. Why it is happening? Again, the same reason. There is a repulsion between the lone pair and the bond pair. As a result, this angle also, which should be 109.5 degrees, is now reduced to 107 degrees. So the point is that here, so one more important point. You are to remember the angle in the case of ideal molecules. You don't have to remember these angles, right? Because it will vary depending on the central atom and the surrounding atom. But you have to remember it for the ideal case. But you should remember this point, that your ideal case will have a greater bond angle as compared to the lone pair inclusion. Now, if I look at different steric number and see that what are the shape and geometry, then there is a list of that. If you are getting a steric number of 3, okay, so here is a steric number of 3. Therefore, your shape will be bent, of course, and your geometry will be trigonal planar. So here your E is representing the pair of electrons, okay. In the second type, we have AB3. So 3 surrounding atoms are there and 1 lone pair is present. This is being shown here. Now, if this is the case, then the shape would be trigonal pyramidal and your geometry would be tetrahedral. You can look it very clearly that it has a geometry of tetrahedral. Then we have 2 lone pairs here. Again, the steric number is 4. In this case also, if you calculate, so the shape would be bent and the geometry would be tetrahedral. See, these two AB2E and AB3E2 are having the same shape, okay, but their geometries are different. One is having tetrahedral and the other is having trigonal pyramidal. Let us move on to the next set of the atoms. So the next set of atoms have 5 as the coordination number. You can see it here. 5 bonds are formed, or you can say 4 bonds and 1 lone pair, AB4E. That will result in a seesaw structure, seesaw shape, okay? And the geometry would be trigonal pyramid, bipyramidal. Why I am calling it a trigonal bipyramidal? You can see on the plane that there is a triangle that is being formed with the help of two B and one lone pair. At the same time, there are two B atoms which are in the collinear phase, and that is creating a trigonal bipyramidal shape. Next is AB3E2, which is having a coordination number of again 5 if you calculate it. It is having T shape. As soon as you see two lone pairs, that means T shape and trigonal bipyramidal. Next is AB5E, where we have octahedral. The steric number is 6. So it will have a square pyramid. Why I am calling it a square pyramid? The 4 B atoms are forming a square and top of that is a B. If you join these lines, you will get a square pyramid. But your overall geometry will be octahedral, including the lone pair. Okay. And the last one is AB4E2, which is having two lone pair. So the geometry would be octahedral, but if we exclude this two lone pair, then its shape would be square planar. So in this way, we have looked upon all types of structures, including the molecules having 0 lone pairs on the central atom and one or more than one number of lone pair on the central atoms. I would suggest you to see and practice this. Once you are practicing this, you don't have to calculate the steric number also. If you are going through 4 or 5 examples, I am telling you, just go through 4 and 5 examples. You will be easily able to calculate the steric number without doing the calculation also. Okay, it's very easy to do. Now, we have already discussed about the polarity of bond. Okay, I have told you about this earlier. But without knowing the molecule shape, we cannot determine the actual polarity. So to do so, I am providing the polarity of some molecules, 2 molecules I would say specifically, with the help of the VSEPR and some help of vector addition. So it's an important part of this 2 slides that I will discuss, which is vector addition. If you look here, you can see a water molecule, okay? What would be the direction of your dipole moment? We have already discussed about it, that your dipole moment has a specific direction as it is a vector quantity. So what would be the direction? It will start from the hydrogen and go on to oxygen. Now, why this is pointed from hydrogen to oxygen? Any guesses? Think about it. What is the reason? We can also take it in opposite way from the oxygen to hydrogen. Remember, I've talked about a convention that how you should put the cross arrow. What was that convention? How do we know that your dipole moment arrow would start from hydrogen and end at oxygen? So it's very simple. If you take one OH bond, the oxygen is having a greater electronegativity. So it will have a delta negative charge, whereas your hydrogen will have a delta positive charge due to difference in electronegativity. As a result of that difference, what will happen? Your dipole moment will start from the positive side, which is hydrogen, and move on to the oxygen. So remember this. Always your direction of dipole moment would be from less electronegative element to more electronegative element, because in chemistry, the dipole moment has direction from positive to negative. Now these 2 individual dipoles can be considered for the 2 OH bonds. But what will be the net dipole moment? It will be the vector addition. Okay, it would be the vector addition of these 2 vectors, and that will result in a third vector. Now, this is the final dipole moment of the H2O molecule. This is a very simple vector addition formula to be used for calculating the direction of dipole moment or the vector addition. And why it is happening? Why all of these things is happening? Because your dipole moment is a vector quantity, and you can add these 2 vectors to give a third resultant vector. From this discussion, we can easily say that your water molecule is polar in nature because it has a net dipole moment on this direction, which is a result of these 2 individual dipole moments. Now let us consider one more molecule, which is BeF2. If you consider the shape of BeF2, then it will be linear in shape. Calculate the steric number. What is the number of valence electron? It is 2. Number of monovalent atoms, again that is also 2. Charge is 0, so 2 plus 2 divided by 2. The steric number would be 2. So it will be linear in shape. Okay. Then what is the next target? Assign the dipole moment. Again, fluorine is more electronegative, so the arrow will start from beryllium and move on to fluorine. Similarly, here the arrow will start from beryllium and move on to fluorine. As both of these surrounding atoms are same, therefore these dipole moments of the BF bond will be same, but they are in the opposite direction. So we can say that these two individual dipole are along BF bond, but they are in the opposite direction. So these vectors are in the opposite directions. As a result, this dipole moment will cancel each other and BF2 will be non-polar in nature. Okay. I hope this is clear to you. So this was all from the theory part. Now we'll move on to the DPP. Okay, so here is your first question. According to the VSEPR theory, the repulsive interaction between the electron pair decreases in which order? So it's very simple. The lone pair will have a maximum repulsion. Then comes your lone pair and bond pair. And lastly, your bond pair and bond pair. Therefore, a correct answer will be first. Which molecule has a trigonal planar geometry according to VSEPR? So let us try to attempt this question. If you consider each of this molecule one by one and calculate the steric number, you will easily get your answer. So first, let us take it for the NH3. If you take the case of NH3, the valence electron is 5. Of course, nitrogen will be taken as the central atom. Okay. So nitrogen is central atom. Now, what is the number of valence electron on central atom? It is 5. Number of monovalent atom, M will be calculated as 3. Therefore, the steric number Sn can be calculated as 1 by 2 multiplied by V plus M. So 5 plus 3. There are no charges, so rest of will be 0. 5 by 3, which is 8, that is 4. 4 was related to tetrahedral. Okay. So we can say that our first molecule is tetrahedral. Let us move on to the next one, which is BF3. Okay. If I take the case of BF3, so boron, it will be the central atom. So this will be the central atom. The number of valence electron will be 3 and the number of monovalent atoms will be 3. Therefore, we can say that steric number would be 1 by 2, 3 plus 3. That is equals to 3. Now, 3 corresponds to tetrahedral. Sorry, 3 corresponds to trigonal planar geometry. Okay. So it would be trigonal planar. So we already got our answer. We don't need to calculate it further. But still, if you want, you can calculate the steric number for each of this. So H2O will have a steric number of 4. Therefore, its shape would be bent. Okay. So H2O looks like this. It has 2 lone pair and 2 bond pair. If you remember our previous discussion, I know it is new to you. So I am telling it to you. So this is having a bent shape. If you consider only the atoms and not the lone pair. If you consider the geometry, then in that case, your geometry would be tetrahedral. Why tetrahedral? Because geometry is totally calculated by using your steric number. We don't have to worry about the lone pair and bond pair. Both are included in the geometry. Similarly, your CH4, it will have no lone pair. Therefore, both the geometry and the shape will be tetrahedral for CH4. Okay, I guess this is clear to you. If you have a doubt, you can ask it right now about any of these. Now, moving on to the next question. Which of the following molecule has a bent geometry? So here comes your next question. We have already calculated for all of this, and we know it very well that your H2O will have a bent shape. Okay. So here it will be shape and not geometry. Okay. So we will consider here shape, because geometry will be tetrahedral, but shape will be what? Shape will be bent. Right? Is it clear? So you know how this question is incorrect, because shape is always bent. Okay. Geometry includes the lone pair also. If you consider the geometry of the H2O, it will be tetrahedral. Moving on to the next question. Which molecule has a dipole moment of 0? So to include the dipole moment, you have to look for the molecules individually. Let us take the case of NH3. If you calculate it for NH3, you will clearly notice that your NH3 is having a which shape? It is having a tetrahedral shape. Now, what will be the order of dipole moment? This will be the direction of dipole moment. And remember, students, a very important point I am telling it here, that for the case of lone pair, your dipole moment will start from nitrogen and move towards the lone pair. So this is always true. Right? So it's very, very important to notice here. Again, I am repeating it, that your direction of dipole moment in case of lone pair would start from nitrogen and move on to the lone pair side. You can see it very well that all of these dipoles are adding together and moving in the forward direction. So the net dipole moment will be upside. Here, similarly for the H2O, we have seen that your H2O has a net dipole moment in this direction. But for the case of CO2, it has a zero dipole moment, because CO2 will be linear in shape and carbon is less electronegative. Therefore, the dipole moment direction will be in this direction, and in here also in the opposite direction, but of the same magnitude, because both bonds are same. So this will result in a zero dipole moment. So we can write mu is equals to 0 for CO2. So we got our correct answer, which is option number C. Moving on to the next question. In the VSEPR model, a molecule with AB4 and no lone pair on the central atom, which will have which geometry? So it's very simple. AB4 means no lone pair, means it will look like this. Okay. 4 bond pairs are there, and we know if there is no presence of the lone pair, then the steric number is simply equals to the number of bonds. So we can write steric number is equals to 4, and steric number 4 corresponds to tetrahedral shape. Now we have attempted all the DPPs.